Welcome to part 1 of my Analyzing WannaCry series. WannaCry was a ransomware attack that caused worldwide mayhem in May 2017. Over 300,000 computers were infected by it, hitting companies like Boeing, Hitachi, TSMC, and Renault. In this video, we will start unpacking WannaCry and look at its basic behavior. In the next videos, we will then look at the ransomware module and the worm module. The WannaCry sample I am using in this video is linked in the description, but please be careful when using it. Try to not encrypt all your files. But to begin, let's see how WannaCry actually behaves. I have set up a basic and outdated Windows 10 VM with some nice pictures and an important document that I absolutely don't want to lose. Now normally WannaCry would spread automatically, but to demonstrate the potential initial infection vector, I will just act as a user and run WannaCry as administrator. We can see that nothing really happens, though after roughly 30 seconds we can see the preview of the photos disappearing and some new files showing up. And then after roughly a minute we get the infamous ransomware dialog telling us that we have 7 days to pay the ransom, otherwise all our files will be gone. We can also not access any of our pictures anymore, and the background was set to this warning. So let's load WannaCry into Ghidra and check out how it works. To import the file, we simply drag the WannaCry binary into Ghidra. Ghidra detected correctly that the binary is a portable executable, and so we can just hit OK. After the import is complete, we double-click WannaCry to open it up in the code browser. We select to analyze the file and enable decompiler parameter ID as well as Windows PE propagate external parameters as additional analyzers. We ignore the warning and start analyzing the binary by taking a look at the functions that were found. In the function list we mainly see unnamed functions and no main or winMain function, so we start looking at the entry function, which is the first function that is called when the executable is launched. If you do a lot of Windows reverse engineering, you probably recognize this code immediately. This is the default entry code generated for Windows executables, and at the end there is the actual call into the winMain function, the actual application main function. We can simply copy over the function signature from the Microsoft documentation, select the correct types, and we have set up the correct signature for the winMain function. Let's go into winMain. Here, the first thing that the eye jumps to below all the stack variables is a curious string. Looks like a URL. Let's look at it. It's http www iuqer and so on and so forth. Let's rename the variable and call it strange URL and also change the type of it to be a C string. Then the next few lines after the URL are a great example of where the Ghidra decompiler fails to detect common compiler output. The 7 lines are just created by 2 instructions, movsd.rep, which is a repeated move statement and commonly used as string copy, and an additional move. If we label all these variables correctly, it becomes quite obvious what this is. I contains 14 and is decreased by 1 on each iteration, and on each loop 4 bytes from strange URL are copied into the memory pointed to by puvar3. Let's rename puvar3 to strange URL copy and also change its type to be a C string. The cast to undefined 4 is just an optimization. Instead of copying 1 byte at a time, 4 bytes are copied on each iteration. If we check where strange URL copy comes from, we can see that it points to a stack buffer. Let's call it strange URL buffer. Let's also add a comment that this is a string copy from strange URL into strange URL copy / strange URL buffer. The next line we're interested in is the call to internet open A. By hovering the function, we can see that Ghidra does not have a function signature for it, but we can again just copy it in from the Microsoft documentation. We do the same with internet open URL A. We copy the signature from the documentation, but wait, the documentation has a small mistake here. The signature says that the function returns void, but further below it says that the function has a return value. After digging into this, it turns out that it actually returns the type hinternet. So let's edit the signature, but when clicking OK we see that Ghidra does not know the hinternet type, so we need to create a custom type. I've looked this up and hinternet is simply a void pointer. So we hit OK and now we can edit the function signature, we paste it in, select the types and change the return type to hinternet. Let's call the value it returns hinternet return. So now if we look at the full line, we can see this just tries to request the strange URL we saw earlier. If the request fails, so when it returns a null handle, it closes the handle and calls a function. Otherwise, it just returns from winmain and by that quits the program. Let's rename the function that is called on failure to retrieve the URL to WannaCry real entry, because it seems that this is where the real stuff happens. Now you might be wondering, what is the function of this URL? It turns out that this URL is the infamous killswitch domain that was discovered and registered by Marcus Hutchins, aka Malware Tech Blog. There's a great interview in the description where he describes that he originally only registered it to track infections and was not aware that it would kill the malware. So let's jump into the real entry. We see some nicely detected stack variables. We also see that the first function that is called is getModuleFilename, which retrieves the path of the executable and stores it in a variable. The next line retrieves argc, the number of arguments supplied into the program. Below that is a check whether we got any arguments. If we did not get any arguments, we run a function and quit afterwards. Let's call this function noArgumentHandler and jump into it. We can see that there are simply two function calls in here, so let's open up the first one. We get a nice clean decompilation result of the short function. We have a sprintf that loads %s-m security as format string and executable path as the string to insert. So we end up with something like this: the path of the executable with -m security as arguments. So let's call this exec with args. Next we see that we get the service connection manager, and if that's successful, we create a service called MSSec SVC 2.0 and Microsoft Center 2.0. We have some flags that basically set up the service to start on boot and with all permissions. The service executable is our WannaCry binary with the -m security arguments. Lastly, it also starts the newly created service. So let's call this function create WannaCry service, and indeed, if we check the services running in our victim VM, we can see that there's a new service called Microsoft Security Center, created by WannaCry. Okay, so let's check out the second function, and this one is a much longer one, but let's simply go step by step. First, we get a handle to kernel32 DLL, and if that's successful, we load 4 different functions from the module, all identified by a string argument. We name all these accordingly, for example, create process A, create file A, write file, and so on. Then there is a check whether the loading was successful, and if yes, we can see that the binary tries to find a resource named 1831. If that's successful, we load the resource, log it, and then we get the size of the resource. Looks good. On the next lines, we again have some functions that Ghidra did not recognize. Let's hope once the decompiler is open source that the heuristics will improve for this kind of stuff. I've also compared this to the output of Reddec, another open source decompiler, and it recognized all of these quite well. Now further below we can see 2 calls to sprintf that don't look quite correct. A call to sprintf with a stack variable as destination buffer and a path as format argument, but no more arguments to fill the actual format string. And by looking into the disassembly, we can see that 2 more arguments were pushed on the stack but not recognized by Ghidra. So what we need to do is overwrite the function signature. We keep the general format, add 2 more char pointer arguments for the 2 %s found in the format string, and we also changed the calling convention to be correct. Suddenly our decompilation result looks much better. We can now see that sprintf creates a string containing the path of taskshape.exe, so let's rename the output buffer to taskshape_path. We do the same on the next line and get a strange path into C Windows QER something, so let's call this QERIU path. In the next line we see that a move file function is used to move taskshape.exe to the QERYU something path that was just created. Then the createFile function pointer that was created earlier is used, but to get a better signature we need to correct its type. We know it's a pointer to the createFileA function, and luckily Ghidra has that type built in. If we adjust the type of createFile to be a createFileA pointer, we can see that createFile is called to create a new task as chexe and returns a file handle. We will call it createdFileHandle. If the file creation was successful, writeFile is called. Let's adjust the type of write file, and we can see that the resource 1831 we saw earlier is now written into taskj.exe. Then the file handle is closed, and we see some more memset and similar code, one of which is actually a string cut which appends /i to the taskj path. Further down, we can again see one of the function pointers being used, this time to create a process. The process created is the just written taskj.exe with /i appended as the argument. Let's give the function we are in a name so we remember what it does, and then let's take a look at the resource that is being extracted and executed. For that, we switch to a terminal and use a tool called wresttool, which is part of ICO-utils and allows extraction of resources from exe files. When we run wresttool on our WannaCry binary, we see that it finds two resources, one of which is named 1831, just as we just saw in the binary. Let's extract that resource and run file on it, and it turns out it's another executable. Before we analyze it in Ghidra, let's take a look at what we know so far. When WannaCry is started, it checks the killswitch URL. If that succeeds, it simply does nothing. Otherwise, it checks whether it was launched with any arguments. If not, it creates a service that will start itself with the -m security arguments. Then it will write the embedded resource 1831 to C Windows taskj.exe and run it with the /i argument. We import and analyze the file with the same options as before, so we simply drag it in, hit import, and then analyze it. This time we start by exploring the strings contained in the binary. The first one we see is an inflate decompression thing, but we can't see any direct reference to it. Then we see an unzip copyright string, and it is referenced to by a function, so let's call it unzip something. Then we also see a lot of file extensions, and these are interesting because they also include the file endings of the files we saw get encrypted earlier. Underneath those we see three strings that very much look like Bitcoin addresses. So let's call this Bitcoin something. And indeed, the one that was shown to us earlier by WannaCry is one of these three. We can also find some crypto-related functions, this part which sounds interesting, and also a string that says WannaCry. Over on the function list, we again see nothing really interesting. So let's jump to the entry point, which again is just the standard entry point. So we again copy in the winMain signature and jump into the main function. In the main function, we see some memset again going on, and the first function call is a call to getModuleFileName, which gets the path of our current executable. Let's rename the variable accordingly. We can also see that the size of the filename buffer is 520, so let's change its type to be a C string with a size of 520. On the next line, we see a function that takes a reference to some global variable. Let's jump into it. Again, some memset going on, and then getComputerName is called, which stores the computer name in a variable. Then we can see a pointer to computer name being created, which is then used in a loop to generate a seed that is fed into srand, which initializes the random number generator. Then some random numbers are generated and put into some calculation involving a char that param1 seems to point to. So let's change the type of param1 to be a char pointer. And suddenly our decompilation looks much better, and we can see that the random number is converted into a string and put into param1. So let's call it random string output, and we will call our function random string generator. We also name the global that is fed into the random string generator as random string. Now the next line gets the number of arguments supplied to the program, and the if clause checks if we got one argument. We see some string that is used in string comp and a reference to some data that looks strange. If we look at it and clear the bytes, we can see that there's actually a C string hidden here, /i, just as we've seen before in the main WannaCry binary. Let's clear the symbol and redefine this as a C string. The next line gets the argument array, and we see that the string comp compares argument 1 with /i. If that comparison is successful, we jump into another function. Again, we see some memset going on that we'll just ignore for now. Then we see a multi-byte to white char conversion that puts the random string into a stack variable. Let's adjust the types and name the variables accordingly. The next line gets the Windows directory, which can be c/ or c/Windows or really anything. Then we have an SW_printf that looks kind of strange. There's not really a format argument, and when we check out the count global used, it does not really look like an integer. So let's clear the data, including the symbol here, and we suddenly see that this is a string with a null byte in between, a Unicode string. So let's redefine this, and now we have a nice format string. Looking back in the decompilation output though, we see that the signature for SW_printf seems wrong. Where the decompiler expects a size, we are supplying a string. It turns out that the SW_printf used by WannaCry is a pre-standardization one that does not take a size as its argument. Once we adjust the signature, this looks much better. A path to c/program data or c/windows/program data is created. Now, the file attributes of that path are requested, and if the directory does not exist, another function is called. The function looks very simple. It takes param1, which is a string, and creates a directory named by it. Then it sets the current working directory to the directory it just created. It repeats that with the string in param2, and then sets the file attributes of the second directory to hidden and system. If param3 was supplied, it puts the directory name into the third parameter, which we call directory out. Also note that it returns 1 on success and 0 on failure. Going back into the calling function, we see that we are creating a directory in c/program data, and in that we create a directory named by our random string. Param1 is used as the directory output parameter, so let's name it current working directory out. If the function failed, it reattempts the same with a different path. The first time c/intel and the second time directly on c/. Let's fast forward over this. Now let's give our function a name, such as create random hidden directory, and go back to the calling function. For some more clarity, let's actually name it create and change working directory to hidden directory, because it will make the following code more clear. If the creation of the hidden directory was successful, it copies itself into that new hidden directory, again with the name of tasks.k.exe. If creation of the new tasks.k.exe was successful, another function is called. If we jump into it, we see that the function gets the full path to our just created tasks.exe. It then gets the service connection manager and attempts to create a service named by the random string we saw earlier. If a service with that name already exists, it will simply try to start it. To ensure that no two instances of the binary are run at the same time, it also attempts to acquire a mutex. We skip over this quite quickly as it's very similar to what we saw before. I forgot to include this on my first recording, so don't be surprised if there are some new symbols. We will get to those later. This is also a great time to look at what we know so far about this binary. 1831.bin is launched with the /i argument by the original WannaCry binary. The first thing it does is create a random string based on the computer name. If it got /i as the argument, it creates a randomly named hidden directory in c/program data, installs itself as a service, and launches itself without any additional arguments. So let's go back into the main function and see what it does when it's not launched with the /i flag. First we see that the file name is parsed to get the path of the file, to which we then set our current working directory. Then we jump into a function that takes 1 as its argument. The first thing we see after going into this function is a string that simply contains software \. Let's call the variable that points to it accordingly. We see some string copy into another variable. Let's call it software string buffer, which is further down used in a concatenation that appends a Unicode string, of which we again need to fix the type. We also see a C string above this, so let's quickly fix that one too. This white string concatenation creates a string that reads as software \1encryptor. Then we see a loop in which we can find 2 HKey constants, one for a local machine and one for a current user. Then a registry key is created based on the constant and the software 1encryptor path we built earlier. Let's store the key in rec WannaHandle. If param1 is 0, then we query the registry and store the value in a variable we will call registry value. If we got a value from the registry, we set the current working directory to it. Otherwise, if param1 is non-zero, which it is in this case, we create a new key in the registry and store our current working directory in it. Let's name the parameter setRegistry and label the function as set or query registry current working directory. Then we jump back into the main function. For the call to the next function, we see something strange in the disassembly. The decompiler only sees one argument, but in the disassembly we see this strange string WannaCry something something being put on the stack. So let's adjust the function signature to also take a C string as second argument. Let's jump into this function, and we see that the first thing it does is look for a resource called 2058. Let's jump into the terminal and use wrest-tool again to see the resources in 1831.bin. And indeed, we find a resource with the name 2058. Let's extract it and run file on it. Turns out it's a zip file, so let's just unzip it. But unfortunately, it turns out it's encrypted and wants a password. But wait a minute, we just saw a very strange string being passed into our function. Could that be our zip password? Let's try it. Let's copy this strange string and use it as a password into unzip. And yes, we've decrypted the secret zip file. Let's check out its contents. I extracted the files into a separate directory, and so let's first run file on it. We can see that we got a bitmap picture, some data, some text, another zip file, and 3 more executables. Let's rename the bitmap and open it up, and we can see it's the background picture we saw earlier in our virtual machine. If we look into the text file, it's a text description of WannaCry and basically the ransom node. Then, last but not least, let's check out one of the data files. It seems to contain 5 .onion domain names of the Tor network and also a download link to Tor itself. We will figure out what this is all about in the next video. I hope you enjoyed this introduction into malware reverse engineering with Ghidra and hope to see you on this channel again soon.